Huh? There's a point you can get, right? Okay. Buffers. Buffers are special solutions that are designed to resist changes in pH. That means if I have a solution that is a buffer solution and I add a little bit of acid to it, and I measure the pH will either not change or else only change a tiny bit. Whereas if I would have taken that same acid and added it to pure water instead, the pH would have plummeted. It would have went way down because it would have become more acidic. Okay? So buffer solutions are very important. We have them in our body. We use them industrially. We use them biologically. They're very important because they help us maintain homeostasis. They help us not go out of whack all the time whenever we get too much acid levels in our body or not enough, and we shift the pH one way or the other. We've got to be able to maintain this nice narrow window of around 7.35, no more than 0.1 either side in the human body. Okay? So we use buffers extensively in our body. Buffers are solutions that resist changes in pH when a small amount of acid or base is added. Now realize they only work up to a certain point. You can't dump in a big jug of hydrochloric acid and expect that buffer to handle it. It's going to become saturated to the point where it can't bond with anything else, and then whatever's left over is going to determine your pH. Okay? So only a little bit. And that's what we come in contact with our body, only a little bit at a time, unless you chug a big thing of Drano or something. So what they will do is there are ions present inside a buffer solution that, for example, if you add hydrogen, it'll latch onto that hydrogen and keep it from floating around, so it won't affect the pH. Or if you add hydroxide ions, there's ions in there that'll grab onto that hydroxide and latch onto it and keep it from floating around so that it doesn't affect the pH. Okay? So they're going to neutralize whatever it is you pour in there. And that's the way that a buffer is going to work. Now, how do you make a buffer? I want you to know these words. Okay, we've seen them before, but I want you to remember these together in this capacity. Buffers are made by mixing together two things: a weak acid and its conjugate base. Now, see if you can think about why. You don't want a strong acid to be your buffer, right? Because a strong acid means it's going to stay dissolved and it's going to release its hydrogen and it's never going to come back together. Likewise, you don't want a strong base. Strong base will do the same thing. It'll set in that solution, separate out into its ions, and stay that way. Now, you could use a weak base and its conjugate acid as well, but more commonly, you get this combination: a weak acid and its conjugate base. A weak acid is something like acetic acid, something that doesn't dissociate completely, but yet you still have, let's see if I can get a picture. Hold on, come back. There we go. What you can have is a situation where, let's take this. This is acetic acid. Okay? Notice that some of these, because it's a weak acid, some of these acid molecules stay intact. The hydrogen and the acetate ions stay together. However, some of them, by bringing in a weak base especially, okay, the conjugate base, well, let's look at this. Acetic acid. What is the conjugate base of acetic acid? That means what is left whenever the hydrogen ion leaves, right? And that could, in theory, accept hydrogen again, even though it probably doesn't. Acetate ions, okay? Hydrogen and acetate ions together make acetic acid, okay? The conjugate base of acetic acid is actually this, okay? This is acetic acid minus its hydrogen. In other words, you could put the hydrogen back on here if you wanted to, and that means it could theoretically accept that hydrogen. If so, then it's a base if it can accept hydrogen. So we've got a weak acid and its conjugate base. But here's what you want to do. What you want to do is to make sure, if you have a weak acid, you're going to have more of this than you are of this right here. Okay? In the case of a weak acid, it's going to stay together a lot better than what it's going to fall apart. What you want to create is a situation where you've got some of it together and you've got some of it apart. But you want to be able to control that. And since you've got more of it together than what you do apart, what you're going to do is pour in something else that will bring in with it this conjugate base. Okay? For example, sodium acetate. It's a salt. If you take sodium acetate and pour it in here with acetic acid, what's important that you got sodium ions floating around, but who cares? They don't do anything. We know sodium stays dissolved. Okay? What's important here is that you have these floating around that are stuck together. Some of those have fallen apart, but not very many of them. Okay? You got a lot of these, and now you've put in a lot of these. Now, how does this work? What will happen if I add hydrogen? Guess what can happen if hydrogen ions come in? It'll connect to these guys, right? In so doing, it soaks up hydrogen out of the solution, locks it up anyway, so that it's not affecting the pH. Because pH is only going to be affected by the free hydrogens that are floating around. Okay? If I add a hydroxide ion to this solution, guess what can happen? That's right. It'll pull off this hydrogen and form what? Water, and leave behind this ion. So what we see in both of those cases is little or no change in the pH, right? Because we're controlling we're buffering the amount of free hydrogens and hydroxides that are being able to spread out in this solution. Now, obviously, there comes a point when you put enough hydrogens in or enough hydroxides in, these guys are all full, they can't work anymore, you're going to exceed what's called the buffering capacity of that solution. All right, now to go back then, the weak acid can neutralize any base that you bring in, and the conjugate base that's present can neutralize any acid that you bring in. That's why you need those two things together. You don't want a strong acid or a strong base because they're not going to neutralize, they're not going to work properly because they're going to stay dissociated. You want something that doesn't stay dissociated that you can form things with. Okay, so little or no change in the pH. So if you take acetic acid and sodium acetate, which was that picture we just looked at, you can make a buffer solution with a pH of 4.75. That means it hovers around. The solution itself maintains pH right around 4.75, if that's what you wanted to do. You can mix equal volumes of 1 molar acetic acid and 1 molar sodium acetate. There's the acid, the weak acid. Here's the salt that will contain the conjugate base. Put those together, you can create a buffer system. Okay? If you add 10 milliliters, just to show you how good this works, if you add 10 mils of 0.1 molar hydrochloric acid, so you add acid to 1 liter of your buffer, and you measure the pH, it'll give you a solution with a pH of 4.75. Okay? Now, if you add 10 milliliters of 0.1 molar hydrochloric acid to 1 liter of distilled water that had no buffer in it, look at where the pH goes to. It'll give you a solution with a pH of 3. So it's a way for us to control and narrow the window of the range of where pH can fluctuate. That's why buffers are so important. Okay? The same truth here. Buffer, it'll hold, if you put some sodium hydroxide, the buffer will hold around 4.75. But if you put that same amount into water, it would shoot all the way up to 11 as opposed to stay at 4.75. So you can see the importance in this. Okay. Make sure you can understand this picture here.